Good day, students. Today we are going to discuss on the topic Raman spectrum and its spectroscopy. So let me share the screen with you. So the Raman spectrum and spectroscopy is my topic today. So today we are going to discuss on this contents, Raman and its theory and basic principle, then Raman spectroscopy, its application, and then conclusion. So you know very well, he is the Indian. Sorry, he is the only Indian to obtain the Nobel Prize in Physics directly. So at first he got he is the first person, and he born in November 7, 1888, November 21, 1970 in southern India. So he is in 1907 he was posted in Calcutta as assistant accountant general. 30 papers he published and the research on acoustics and optics. He is a pioneered Indian science, founded Indian Academy of Science, found Indian Journal of Physics. Still, Indian Journal of Physics is alive, and you can communicate your research papers to Indian Journal of Physics, which is coming under Springer Publications. He won Nobel Prize in 1930 for physics, discovered the great Raman effect. So no scientist from India have achieved this greatest, one of the greatest contribution to the society. So he is the only scientist who attained this privilege in our country. Then Subramaniam Chandrasekhar and many other scientists, S.N. Bose, and there are some scientists also from Calcutta, and they also achieved one of the biggest attainment in the society, that is the Nobel Prize. But he laid the seed for uh, the Nobel Prize, then how to achieve Nobel Prize and how to think a problem. So how to find a solution for a problem. So he's the pioneer physicist, and he found this Indian Academy of Science. So still Indian Academy of Science is publishing lot of research papers. It's training a lot of students, and it's one of the major governing body of our country. So let us come to Raman spectroscopy. The basic principle of Raman spectroscopy is when the laser source hit on a molecule, what will happen? The molecule may undergo reflection, absorption, or scattering. So when it scatters from atom, so there is a uniformity. So Raman identified from the bonds, the scattering will differ based on the oscillating dipole of a molecule. So the Rayleigh scattering occurs when incident electromagnetic radiation induces an oscillating dipole in a molecule when it is re-radiated at the same frequency. The Raman scattering occurs when a monochromatic light source of light, that is a laser, is scattered by a molecule, and the scattered light has been weakly modulated by the characteristic frequencies of the molecule. So the vibration always linked with frequency. So this characteristic frequency, he classified the frequency, and based on the frequency classification, he determined and he evolved some solutions. So the basic principle of Raman spectroscopy is that when a monochromatic radiation is incident upon a sample, then this light will interact with the sample in some fashion. That is, it may be reflected, absorbed, or scattered in some manner. It is a scattering of radiation that occurs, which gives the information about a molecular structure. So Raman spectroscopy is based on a scattering, The sample is irradiated with a coherent source, typically a laser. Most of the radiation is elastically scattered, called Rayleigh scatter. A small portion is inelastically scattered, that is a Raman scatter, composed of Stokes and anti-Stokes portion. This latter portion is what we are particularly interested in because it contains the information in which we are interested in. So this is the basic principle of Raman spectroscopy. So spectroscopy is always based on the light frequencies. So how much light falls on it and how the light categorize the molecules or atoms. So how what is the effect of light when it hits a sample, that is a molecule. So how what is the effect based on light we are going to obtain it. That is a spectroscopy. It can create some spectrum of lines. So that spectrum will give the complete information about the object or sample. So this is light when scattered by sample at the various angles by momentary absorption to visual state and the re-emission. These are the energy levels and 1, 2, 3. So there's no change in the electronic states. So you know the equation E equal to H nu. So H is the Planck's constant, and U is the frequency, and E is the energy. When energy absorbed by the molecule from a photon of light not quantized, what will happen? It produces the Rayleigh scattering E equal to H nu. But there are some inelastic uh, collision happens, that is in terms of Raman scattering E equal to H nu. There is a change in energy. If the change is positive, we call it as a anti-Stokes line E equal to H nu plus del E. And if it is negative, the energy will be H nu minus del E. There is a change in energy. So there is an infinite number of virtual states Raman identified. These states of matter, we call it as a Stokes and anti-Stokes line. So some scattered emissions occur at the same energy while others are written in a different state. So Rayleigh scattering and Raman scattering. So Raman scattering, net change in energy HV in greater than or less than HV out. So there is a Rayleigh scattering, there is a no change in the energy. But in Raman scattering, there is a change in energy. So we can see the change in energy will be H nu plus or minus del E. So two types of Raman scattering. So the previous slide, you can see this elastic collision between a photon and molecule results in no change in energy, that is Rayleigh scattering. Inelastic collision between photon and molecule results in a net change in energy. Okay, so two types of scattering. You should remember whenever you are studying this Raman effect and its Raman scattering, you need to remember the Stokes and anti-Stokes lines. So Stokes and anti-Stokes lines are formed only during this Raman scattering, not in Rayleigh scattering. So the Raman scattering, there is a change in energy. So Stokes line E equal to H nu minus del E, and anti-Stokes line E equal to H nu plus del E. So we can see the Raman frequencies shift and IR absorption peak frequency are identical. So the resulting Raman spectrum will be obtained like this. So this is the energy levels, and you can see the Stokes and anti-Stokes line. So this anti-Stokes line, which has the higher energy. So these are the different, that is Rayleigh scattering, greater than Stokes and greater than anti-Stokes. So the heavy arrow on the far left depicts the energy change in the molecule when it interacts with the photon. The energy in is equal to the energy of photon h nu. The second and narrower arrow shows the type of change that would occur if a molecule in a first vibration level of electronic ground state. The middle set of arrow depicts the change in the that produces Rayleigh scattering. So these are the you will have the clear understanding that is Rayleigh scattering. There will be no change in energy, and the Raman scattering. There is a change in energy, that is Stokes and anti-Stokes line. So equal to h plus or minus del E. Okay. So the ratio of anti-Stokes line to the Stokes intensity will increase with temperature because a larger fraction of molecules will be the first vibrationally excited state under these circumstances. Okay. So the Nobel Prize he obtained in 1930. And what happened? Why can't we attain this Nobel Prize after 1930? So some of the Nobel laureates of our country or from Rabindranath Tagore, who got the first Asian and non-European Nobel Prize, received his Nobel Prize in Literature in 1913. And some of the privileges from our Indian citizens are Mother Teresa for Peace Prize year 1979. Mother Teresa for his recognition of bringing out the people who are suffering from diseases. And Amartya Sen in 1998, he got his Nobel Prize in Economics. So for his contribution to the welfare of the country in economics. And then, do you remember one of the important personality who struggle against the suppression of children and young people to attain education? So his name is Kailash Satyarthi. In 2014, he obtained Nobel Peace Prize. And some of the Indian-born scientists, and that is a British India scientist. In 1983, Subramaniam Chandrasekhar, 1983, he obtained for physics. Then 2009, USA-born, Indian-born USA scientist in chemistry, Venki Ramakrishnan. In 2009, he obtained the Nobel Prize for his contribution in structure and function of ribosomes and macromolecular crystallography. Then Abhijit Banerjee, so he is also an Indian-born US scientist, that is in economics for his experimental approach to elevating global poverty. In 2019, he got the Nobel Prize in economics. So these are some of the renowned personalities of India who attained the Nobel Prize. But after some of the there are some unsung heroes also. Indian side, we are having some unsung heroes. That is the Saha scientist, Saha, that is Magnan Saha, who is a pioneer astrophysicist. He introduced the world to thermal ionization equation, better known as the Saha equation, which demonstrated the relationship between elements ionization to temperature and pressure. So he is one of the unsung hero. And Homi Jahangir Baba is the father of our nuclear program. He is an Indian nuclear physicist who was nominated 5 times consecutively for a Nobel Prize in Physics between 1951 and 56. But unfortunately, he didn't attain the privilege. However, he got esteemed prizes, and he is one of the man behind Tata Institute of Fundamental Research and Baba Atomic Research Center. Homi Jahangir Baba. Then Satyendranath Bose, and he found the Bose-Einstein condensate along with Einstein. Uh, he born in a middle class family at Calcutta. So remember, Calcutta gave lot of personalities who achieved the top level awards and prizes in the world. So Calcutta is one of the prominent place. See, there you can see the biggest library in the country. So this Calcutta, which brought a lot of things in our country. So Bose, who born in 1894, 1st January 1894, he topped his bachelor's and master degree in mathematics from this Presidency College, and his papers were inspired by Albert Einstein, and they combined together and published various papers, and he is one of the esteemed physicists in our country. He is also one of the unsung hero. Then one of the important discovery, that is in medical physics, Nobel Prize in Medicine, one of the unsung hero, that is Ubendranath Brahmachari. He is one of the unsung hero in the medical physics. So then Narayanan Ramachandran in biochemistry, he is one of the unsung hero. Thiruvengadam Rajendram Sheshadri, he is a Padma Bhushan awardee in Indian chemist, and he is a Nobel Prize nomination in chemistry in 1966, but unfortunately he didn't attain the privilege. And in material science, in our country, the living scientist C.N.R. Rao is one of the unsung hero of the Nobel Prize. So, what is your opinion, students? Will we attain a Nobel Prize by 2030 or 35? Is that possible to attain? So, one thing I want to say at this moment of time. So, it is a way of thinking how to attain Nobel Prize and how to achieve this privilege. That is, it is the way of thinking, how you are seeing the problem, and how you are approaching a problem. So that is more important than anything. Than anything. Whenever you are approaching a problem, that should be different and that should be unique. Then only you can get the way of thinking. So Raman, Sir C.V. Raman, uh, so he is one of the important and most privileged Indian citizen who win Nobel Prize. So, as an individual, that can make a definite contribution to the society, but in the large scale research infrastructure, we are lacking. So, we should enhance our infrastructure, and we should have many collaborative projects with abroad universities, esteemed universities like Harvard, Cambridge. So many abroad universities, they are collaborating, willing to collaborate Indian scientists. Can you say what will come into your mind when we think of India? For example, Japan, if we are thinking about electronics, so the quality of electronics. And China, if you are thinking, we can see the quantity, how much quantity we can obtain. For 100 rupees, you can buy a lot of toys. But in India, and similar to German, said that is Germany, you can see the technology. So, for example, cars, so automobile industry, so manufacturing industry. So, lot of things are coming. That is a brand. That there is a different brand, definite brand for a country. What is our brand? Can you say what is the brand of our country? So you should set the brand of our country, then only our companies and our industries and our research will touch the peak. Unless we don't have the privilege, so we will never attain this. So we should collaborate with the international universities and colleges. And students, you should enhance your research area, and you should study a lot of things. Because our platform is very low, and we are studying only the basic things. This is a fifth standard study, that is a Raman spectroscopy. We can, if we are seeing the international syllabus, it will be from 6th to 10th. So our standard of studying, our platform is much lower than the international standard. You should enhance your academic capabilities and research abilities. So all these things you need to get into it. Okay. So this is I want to say at this moment of time. So let us get into the instrumentation part. So instrumentation part, which contains the um, laser source which falls on the sample cell, and in which there is a wavelength selector, and which falls on the radiation transducer, and then it falls on the computer and the radiation transducer, which collect the information, and this electronic information will be going to the computer data system. So here optics plays the major role. That is, it should be the spectrometer to select the wavelength, and the laser source when falls on the window. There is the iris diaphragm, and the scatter collector mirror and excitation collector mirror are there. The spectrometer entrance is there. So the wavelength selector will be the filter or a spectrometer. Nowadays we are using not the spectrometer, the electronic filters that can filter the particular wavelength. So the detector will be the photodiode. The photodiode is very sensitive. When light hits on it, it will detect and it will convert that light into electrical signals. So that is the concept of photodiode. So the instrumentation for modern Raman spectroscopy consists of three major components: laser source, a sample illumination system, and a suitable spectrometer. So the sources used in modern Raman spectrometry are nearly always lasers because of their high intensity is necessary to produce the Raman scattering. And Raman scattering of sufficient intensity to be measured with a reasonable signal to noise ratio. And next, because of the intensity of Raman scattering, there is the fourth power of frequency, argon and krypton ion sources that emit in blue and green region of the spectrum have, and it has the advantages over other sources. Some common laser sources for Raman spectroscopy are argon ion laser, krypton ion laser, helium laser, and photodiode of 785 or 830 equivalent, neodymium YOG laser. YOG means yttrium aluminum garnet laser. So sources used nowadays are laser because of high intensity and its coherence. How much coherent it will be. So sample illumination system. So the liquid samples, the major advantage of sample handling in Raman spectroscopy compared with infrared arises because water is a weak Raman scatter but a strong absorber of infrared radiation. Thus, aqueous solution can be studied by Raman spectroscopy but not by infrared. This advantage is particularly important for biological and inorganic and in studies dealing with water pollution problem. Yes, especially I want to talk about this water pollution problem at this moment of time. Because, see, I'm reading the first line again. A major advantage of sample handling in Raman spectroscopy compared with infrared arises because water is a weak Raman scatter but a strong absorber of infrared radiation. Thus, aqueous solution like water can be studied by Raman spectroscopy but not by infrared. So, as infrared is being absorbed, infrared radiation will be absorbed. That's why when you expose this infrared radiation to water, the water will heat up. So, this is one of the greatest advantage to study what is the contamination in the groundwater using this Raman spectroscopy. So as I already told you about the microplastics, so this Raman spectroscopy combined with Fourier's can be used for analyzing these microplastics. So nowadays we are not talking about microplastics, we are talking about nanoplastics, because nanoplastic which cannot be filtered by our biological system, and it enter the bloodstream directly, and it will get into the bloodstream and produce and creating a lot of problems in terms of various diseases like cancer and other diseases. So this water pollution can be identified using this Raman spectroscopy analysis, but it's a complex setup. I wish our students, if you want to file a patent in this, you can create a handy Raman spectroscopy machine to analyze the groundwater. For example, you can have the mobile phones, and you can connect the device with the mobile phone, and you can dip that device in the drinking water which you are going to consume. That it will analyze the values, and it will be displayed in your mobile phone like a spectrum or a value, and it will show you how much contamination and contaminant particles are there in the groundwater. It can analyze it. I need to have the handy nanoplastic identifying machine. So if you want to file a patent, it will be one of the wonderful contribution to the society. I wish to come forward. I call upon all the students to work on this area, to file a patent on this, so that our future generation will be saved from these nanoplastics. So it is an open call to everyone. So if you wish, you can work on it. Already we discussed in the class so about the microplastics and nanoplastics, and one day, if possible, I will give you the elaborate discussion on this microplastics. So this microplastics mainly uh, that is the major pollutant that's harming. It's not biodegradable, so it's harming our biological system. So you should know about this. What are all the harmful effects of this plastics? So it is necessary to everyone to know about the microplastics and nanoplastics. So that's why I'm insisting again and again. So we don't know why cancer is disease like cancer is coming to small children. We don't have enough exposure to the environment, but the small children like 1 or 2 years, so it got affected by cancer, different kinds of cancer, blood cancer. We don't know what's happening behind. So it may be due to the microplastics, as the research says that it is due to the some microplastics and nanoplastics are entering into the placenta of the human womb. So there may be the possibility for occurring cancer for a newborn child. So this is a area of research. This is an open call, and I need a handheld machine to determine the microplastics and nanoplastics in drinking water, which you are consuming daily, at least 3.5 to 4.5 to 5 liters every day. So it is necessary to have the handheld machine that can be attached to your mobile phone to analyze the spectrum. So it's an open call. I wish someone will come forward and we can file a patent based on this. So coming back, so to the instrumentation part of Raman spectroscopy, there is solid samples. Raman spectra of solid samples are often occurred by filling in a small cavity with the sample after it has been ground to a fine powder. Polymers can be usually examined directly with no sample pre-treatment. So the gas samples normally contain glass tubes, 1 to 2 centimeter in diameter and about a 1 mm thickness. Gases can also be sealed in small capillary tubes. So these Raman spectrometers were similar in design and used the same type of components as the classical ultraviolet and visible dispersing instruments. Most employed double grating systems to minimize the spurious radiation reaching the transducers. Photomultipliers served as transducers. Now, Raman spectrometers being marketed are either Fourier transform instruments equipped with cooled germanium transducers or multi-channel instruments based upon charge-coupled devices. So this is the original, that is the actual picture of a Raman scattered image. So the typical Raman spectrum is like this. And there are different types of Raman spectroscopy: resonance Raman spectroscopy, surface enhanced Raman spectroscopy, micro Raman spectroscopy, nonlinear Raman spectroscopic techniques. And this is the very important spectroscopic methods combined with Fourier transform. Since this instrument, we call it as a FT Raman instrument. That is often a neodymium log laser is to excite the sample so that the excitation energy is lower than the absorption band energies of organic systems like water or aqueous solution. So fluorescence is then minimized. Instruments may be combined with a microscope or optical fiber so that scanning over uh, a small area it can be easily performed using this spectrometer. So Fourier transform Raman spectrometer will be appearing like this. And some of the examples and applications of this Raman spectroscopy is it's often superior to infrared spectroscopy. And in addition, the vibration energy of metallic on bonds are generally in the range of 100 to 700 per centimeter, a region of infrared that is extremely difficult. And Raman studies are potentially useful source of information concerning the composition, structure, and stability of coordination compounds. And it can study the organic species. Then quantitative application, that is Raman sampling devices are not subject to attack by moisture and small amounts of water in a sample that do not interfere with that. So the major application is the biological application. So we can apply Raman spectroscopy to the biological system. So this biological system has the greater advantage so that it can understand the environmental sensitivity and spectral analysis. So that's all today. But before winding up, I want to deliver some interesting facts in Sir C.V. Raman life. That is, Raman quit his government service. He is appointed as the first Paley Professor of Physics at the University of Calcutta in 1917. Then, while he was teaching at the University of Calcutta, Raman continued his research at the Indian Association for Cultivation Science in Calcutta. So he became the honorary scholar at the association. Then, Indian Association for Cultivation Science, Raman did a groundbreaking experiment that eventually earned him the Nobel Prize in Physics. So when he was researching in cultivation science, he found the Raman effect. So he discovered the evidence of quantum nature of light by observing the scattering of light, an effect globally known as Raman effect. The day is celebrated as the National Science Day, and he is one of the greatest scientists. And he had a collaboration with the experimental physicist K.S. Krishnan. He is who is the co-worker and Raman's co-worker, and always he mentions in a Nobel acceptance speech, and he mentioned K.S. Krishnan's contribution. He is the discoverer of atomic nucleus and proton. So that is the discoverer of atomic nucleus and proton. Dr. Ernst Rutherford referred to Raman spectroscopy in his presidential address to the Royal Society in 1829. Raman was acknowledged by the society, and he was also presented with the knighthood. And Raman had been hoping for a Nobel Prize since 1928. After 2 years of wait, he bagged the award for his work on scattering of light for the discovery of Raman effect. He was so eager that he had booked tickets to Sweden in July to receive the award in November. Raman was first Asian and non-white individual to win a Nobel Prize in science. In 1932, Raman and Suri Bhagavatam discovered the quantum photon spin. This discovery further proved the quantum nature of light. When asked about his inspiration behind the Nobel Prize winning optical theory, Raman said he was inspired by the wonderful blue nature of the Mediterranean Sea while he was going to Europe in 1921. So when he was traveling, so basically all the scientists they were admired by nature. So you should admire by nature. So how nature works, how the laws of nature works, and how beautiful the nature is. You should be the lover of nature. So when he was asked about his inspiration, he told the wonderful blue nature of the Mediterranean Sea, which inspired him to make the contribution in the optical theory. So now Raman, not only as an expert on light, he also experimented with acoustics. That is, he's the first person to investigate the harmonic nature of sound of Indian drums such as tabla and the mridangam. On his first death anniversary, Indian Postal Service published a commemorative stamp of Sir C.V. Raman with the reading of his spectroscopy and a diamond in the background. He was also awarded the Bharat Ratna in 1954. So these are all some of the interesting facts about Raman. And today we are winding up the session with these inputs. So I hope you enjoyed the session, and I wish uh, the students to post queries and comments in the chat box. And if you have any queries or any questions in Raman effect or anything related to Raman, we will discuss. And you can post your queries in YouTube comment section, or else you can post your comments and suggestions in the classroom also. So three important questions are there in this Raman spectroscopy. So two more questions will be coming from what is the Raman effect and what are all the applications, and five more questions. So or 7.5 more questions, that is explain Raman effect. You have to write the principle and write the energy level diagram and instrumentation part. If they are asking for instrumentation for construction and working of a Raman spectrometer, you need to draw the diagram of the spectrometer. And 12.5 mark question or 10 mark question. So discuss Raman effect, Raman spectrometer, and its application. So mainly the application it is in the biological side in the organic species. So these are all some of the important questions. You should write whenever you are writing Raman effect. You should remember Stokes and anti-Stokes line. That is the energy level. E equal to h nu plus or minus del E. Okay, that is more important. Whenever you are writing it, you should mention this Stokes and anti-Stokes line. Okay, you should compare this Rayleigh scattering also. There is no change in the energy. Okay, these are all some of the important points I want to convey to you. So all the best. Uh, just to throw light on this topic and think over about microplastics and whatever things which I conveyed in the class today. So think about it, and you have to change the uh, way of thinking. So you have to transform. This is the time for transition. So you have to transform your mind to how to think. So you should remember. I hope you will remember all these things, and in future definitely uh, one or two or many can come up with the Nobel Prize in the future. I hope. I hope so. Are you believing in you? If you believe, if you have a strong belief in you, definitely you will achieve it. I hope my students can do it. Definitely you will do it one day. Okay. With these words, I'm winding up. Thank you for joining me, and I'm very much thankful and grateful to Raman, Sir C.V. Raman, who is one of the pioneered physicists, and he led the greatest contribution to the society. I wish you students, you should come forward, and you can also do major contribution to the society. All the best. Thank you so much. Thank you.